Okay, so we are back here to finish off the peripheral nervous system. I know it was hard because the lecture on the spinal cord gets kind of intermixed with the peripheral nervous system because it's hard to talk about the spinal cord and not talk about the nerves that innervate it. So I know that these lectures kind of get blended together. But hopefully we can finish it off here and kind of make sense out of all of it. So again, we're going to talk primarily about the peripheral nervous system today and mostly the sensory and motor portions of the peripheral nervous system, which is the peripheral nervous system. So again, when we're talking about the peripheral nervous system, we're talking about the stuff that is going to link our central nervous system to and from the outside world, okay, to the world outside our body as well as to the world inside our body. So this is going to consist of all these neural structures that are going to and from the brain and the spinal cord. So again, this is going to be our sensory. So we're going to talk about our sensory receptors and our sensory neurons. We'll talk about that. Our sensory neurons are going to be our transmission lines, right? Taking information to the spinal cord and the brain. So taking it to the central nervous system. And I'll kind of remind you, we've already talked a little bit about the repair, but I'll kind of remind you of that. And then we're going to talk about, again, that information that's being sent out of the central nervous system through the peripheral nervous system. And that's through, obviously, your motor neurons. Okay, so we'll talk about our motor endings and our motor activity. And then we already talked about reflex activity because I felt like that went really well with the spinal cord because the reflexes go through the spinal cord, even though obviously, again, part of your peripheral nervous system has to be part of the reflex. So it's really hard to talk about reflexes with just the peripheral nervous system or just the central nervous system because really it's a mix of the two because you have sensory going in to an integrating neuron, right? That's in the central nervous system and then a motor neuron going out. And that sensory neuron and the motor neuron are part of the peripheral nervous system. So again, we already went through those reflex activities, so I'm not going to rehash them here. But if you have any questions, of course, just let me know. So as a reminder, again, we're in the peripheral nervous system here. Central nervous system is just our brain and the spinal cord. So our peripheral nervous system is going to be divided up into our sensory afferent division and our motor efferent division. And if you ever forget afferent versus efferent, just remember, guys, efferent is always exiting. So our motor efferent neurons are exiting, right, the central nervous system and going out into the peripheral nervous system. So that's, I think, the easiest way to remember that motor neurons are efferent because they're going, again, exiting the central nervous system and going to your effectors like your muscles. Now, if we were to just look at, and we're going to primarily in the beginning talk about the sensory division, and then towards the end we'll talk about the motor division. But we've already talked a lot about the motor division because we've talked about the somatic nervous system and the autonomic nervous system. Those are the two divisions of the motor division. So remember that our somatic nervous system are going to be all of those motor neurons that are innervating our skeletal muscles, those ones that are under voluntary control. And then our autonomic nervous system is going to be all those motor neurons that are innervating viscera organs, right, that are not under our control. It's like what I like to call automatic, which is hopefully will help you make sense of autonomic nervous system. These are the ones that are under involuntary control that you're not thinking about and your body is automatically taking care of. So again, the fact that your heart's beating and that you're breathing. Thank goodness we don't have to think about those things. I'm always thankful for my autonomic nervous system because I always say I would probably forget to breathe or forget heartbeat. I, get busy with other things. And so thank goodness we don't have to remember that. We can thank our autonomic nervous system for that. Now, our autonomic nervous system is then broken up into our sympathetic division and our parasympathetic division. And that was what our entire autonomic nervous system lecture was about, right? Our sympathetic being our fight or flight, and our parasympathetic being our rest and digest. So if you need a review of those, go back to that autonomic nervous system lecture. Or if you haven't watched that lecture yet, make sure that you get to that lecture. The autonomic nervous system is fascinating. So hopefully you really enjoyed that lecture. Okay, so let's talk about sensory receptors and sensation. So again, obviously our sensory receptors are gonna be these specialized receptors that are gonna be responding to stimuli in our environment, okay? Either in our internal environment or external environment, okay? And remember that activation of these sensory receptors is going to result in graded potentials, okay? And so that's why we can have multiple stimuli coming in, right, to this sensory receptor. And if we get enough of that stimuli and enough of a graded potential, then it can actually trigger an action potential or a nerve impulse, okay? And so really, these sensory receptors kind of act as translators for the nervous system, taking again this information, this stimuli from, the outside world, or even again from our internal environment, and translating that into a nerve impulse, okay? So we like to kind of say that these are the translators for the nervous system. So we're going to talk a little bit about sensation and perception, okay? And I'll come back to this in a little bit too, but I just want to introduce it again here. When we're talking about sensation, we're talking about simply our awareness of a stimulus. So this is going to be where those sensory neurons are taking information to that primary somatosensory cortex in our brain. Remember all that there. And that's going to give us an awareness of that stimulus. We are aware that our fingers are cold, okay? So we're aware of that sensation. And then the interpretation or meaning of that stimulus is what we call perception. And that's going to happen in that somatosensory association area behind that primary somatosensory cortex, right? So this is going to be, our ability to go, whoa, my fingers are too cold and I could potentially get frostbite and I don't, want to do that. So maybe I should do something about that. I should warm them up or put them in my pockets So that's the difference between sensation and perception. Sensation is just your awareness that, hey, I have that sensation happening. And then perception is your interpretation of that, again, sensation. So let's go back here and we're going to talk about our receptors. And of course, there's lots of ways, to classify sensory receptors. We don't just have one way to classify them. And it's not because we're trying to be complicated. It's just because sensory receptors are so different and complex. So there are 3 different ways that we can classify them. We can classify them by the type of stimulus, by where they're located in the body, and also by their structural complexity. So let's first talk about how we classify them by our stimulus type. So mechanoreceptors, and you guys probably remember these because we talked about these already, thankfully. So mechanoreceptors are going to be responding to some physical change that you're putting on that receptor. You're mechanically or physically changing the shape of that receptor. And so you might respond to touch or pressure, vibration, stretching that. And what that does is, remember, that mechanically opens some of those gated ion channels. So again, by doing that, the mechanoreceptors, you can mechanically open some of those gated ion channels, okay? And so you're literally again, pushing, that pressure is pushing on them to open, or that vibration or stretch. So those are what mechanoreceptors are doing. Now, thermoreceptors are going to be sensitive to changes in temperature. So, and we're going to talk about this because you have different thermoreceptors for cold versus warm. We also have photoreceptors. As you can guess, these photoreceptors are going to be in our eye, in the back of our eye, called the retina, which we're going to talk about in the next lecture on the special senses. And of course, these photoreceptors are responding to light. Okay, pretty easy, right? Chemoreceptors, what are they responding to? You got it, chemicals, right? So these are pretty easy. So examples of things that are going to respond to chemical changes are going to be your sense of smell, your sense of taste, right? That's a chemical change that's occurring. Changes in your blood chemistry. We have chemoreceptors that will pick up those changes in our blood chemistry because it's very important, right, to maintain homeostasis in our blood. So we have chemoreceptors, and then lastly, we have nociceptors. Nociceptors are going to be sensitive to pain-causing stimuli. So we already talked about these, and we talked about the substance P being the neurotransmitter. But what we really haven't talked about, and we'll get into it, is that examples of when these pain receptors will be triggered will be in things like extreme hot, extreme heat, or extreme cold. So we'll talk about thermoreceptors go up to a point, and then once you pass that point, like it's too hot or it's too cold, you actually trigger nociceptors, which are your pain receptors. Or excessive pressure may trigger your nociceptors. Inflammatory chemicals, things like that, will trigger our nociceptors. So those are the ways that we can classify our receptors first by stimulus type. Okay? We can also classify our receptors by where they're located. So we've got exteroceptors. So just think about the term extero, right? It makes you think of X outside of the body, right? So an intero would be like inside of the body. So EX, you can think of like exit outside of the body. So exteroceptors are going to be these receptors that are responding to stimuli outside of the body. And these receptors are primarily going to be things like in the skin for touch and pressure, temperature, picking up the temperature on, again, your skin. Again, any of those types of receptors that you're going to find really on the surface of your skin. Or at least in the dermis, are going to be those exteroreceptors. And even pain, you've even got pain receptors there at the surface as well. And then most of your special sense organs. So vision, touch, smell, hearing, taste. Again, these are all responding to outside stimuli, right? Vision, again, is responding to, again, because it's the photoreceptor, so it's an exteroreceptor and a photoreceptor, because it's responding, again, to light from the outside, right? Same with smell here, it's responding to, it's got chemoreceptors, right, that are responding to chemical changes in the outside, so it's an exteroreceptor. So hopefully that kind of helps you with what an exteroreceptor is. Now, interoreceptors are also called visceroreceptors because they're internal, right? And so what's internal? Your viscera, your organs. So these are, it's pretty easy. Again, you don't have to do a lot of memorization here to put together that interoreceptors are going to be responding to, again, stimuli that is occurring inside your viscera, inside your organs and your blood vessels in your body, okay? So our interoreceptors are going to be, sensitive to chemical changes that are occurring in the blood, whether or not you have too much glucose or not enough glucose. You've got chemoreceptors in your blood vessels, in the walls of your blood vessels. Tissue stretch. Is your bladder stretching? Is it getting full? You're going to, again, have interoreceptors in the bladder to detect that. Temperature changes internally. Again, you have thermoreceptors inside that are interoreceptors to detect that. So, and it says sometimes they cause discomfort, but usually the person is unaware of the working. So usually, every once in a while, you get some discomfort that are caused by these receptors internally, but most of the time you're unaware of these receptors because you don't feel them and you're not consciously, aware of them. So this is kind of a nice little diagram. It tells you interoception helps me feel when I'm thirsty, lets me know when I have to use the potty because your bladder's been stretched, and tells me when I've eaten too much. So those are the types of things that interoreceptors are doing, okay? And then proprioceptors. So you probably remember proprioceptors. These are going to, again, give us an awareness of kind of where our body is in relation to what's around us, okay? So it's going to respond to stretching our skeletal muscles and our tendons and our joints and our ligaments and connective tissue. So again, that helps us have an awareness of where our limbs are in comparison to the rest of our body. And that is going to inform the brain of our movements. So this is kind of a cool diagram, right, of giving us some of that input for proprioception. So again, the brain is interpreting all of these kind of proprioceptors. We have proprioceptors that are going to be in the inner ear that are going to send information about rotation, acceleration, position of our body, right? Our eyes will even send some of that information, again, back and act as some proprioceptors there. So we have lots of stretch receptors in our skin and our muscles and our joints, again, that are going to send information about the position of those body parts. Okay, so this gives us an awareness, a spatial awareness of where our body is. Okay, so now the third way we can classify receptors is actually by their structure. So the majority of sensory receptors belong to kind of one of two categories. So we have what are called kind of our general senses, our general sense receptors. And these are going to be basically everything except for our special senses. And then our second category is going to be our receptors for our special senses. So our general senses are going to be these kind of modified dendritic endings of our sensory neurons. So remember the dendrites coming off of the cell body. We have these modified dendritic endings of our sensory neurons, and you'll kind of get to see this in a minute. And these are going to be found throughout our body. They're going to monitor the majority of our sensory information out there. Okay, again, everything except for the special senses, basically. And then the receptors for our special senses are going to be, again, remember, our special senses are going to be associated with taste, hearing, our sense of equilibrium in the inner ear, vision, and our sense of smell. Okay, so those are going to be our special senses. So they're all going to be housed in these very complex sense organs. So when we talk about our special senses, these are, again, going to be housed in these very special organs. So let's first talk about our general senses. And then, of course, we're going to have a whole chapter dedicated to the special senses, which are really fun to talk about. So simple, again, receptors for our general senses are going to include things like for tactile sensation, touch, pressure, stretch, vibration, our thermoreceptors for temperature, our nociceptors for pain, and again, our receptors for what's happening in our muscles in terms of stretch and things like that. So what's interesting about our general receptors is there is no one receptor, one function relationship. Again, remember that these receptors, right, are working on graded potentials, and they can actually respond to multiple stimuli. So they don't just have to respond to temperature, but maybe some of these receptors respond to temperature and pain, okay? So again, there is no one receptor, one function when you're talking about the general senses. Now, we can break up, you might say, well, how did we get 3 categories of receptor structure? Because so far I've only talked about 2. And that's because we can break up our general sense receptors into our non-encapsulated free nerve endings or encapsulated nerve endings. And it's going to be just like it sounds, okay? Obviously, this is going to be a non-encapsulated free nerve ending, right? And then here, something like our Meissner's corpuscle is going to be encapsulated in a corpuscle, okay? So it's going to be within this capsule. So it's going to be just like it sounds. Same here with something like our Pacinian corpuscle, also called the lamellar corpuscle, okay? So let's first talk about this first category, the non-encapsulated sensory neurons. So, or sensory receptors, sorry. So we have these non-encapsulated sensory receptors. And again, just like we talked about, these are going to be, a lot of these you're going to find in the skin. And you'll see, again, they're going to be detecting, and most even body tissues. You'll find them even in muscles and things like that, detecting stretch or tendons and ligaments. So you're going to find you're going to find these really throughout the body. You can find them in the epidermis. You can find them even in your cornea. You can find them, again, in most body tissues. And these, like we just talked about, they're going to be kind of the bulk of our non-encapsulated sensory receptors. They're going to be thermoreceptors, chemoreceptors, mechanoreceptors, nociceptors, okay? So they can detect whether or not we're warm, or cold, or itch, or our pH is off, or again, we're being pushed on too hard, or we, have pain. So those are going to be those types of receptors. We also have, do you remember those tactile Merkel discs that we talked about way back when we did the integumentary system? So again, these are just going to be these tactile receptors. And the reason that we're going to talk about them is that they adapt slowly for light pressure. So we'll talk about these are rapidly adapting for light pressure, and these are slowly adapting. I know I haven't talked about adapting yet, but we're going to get there. So that's why we're going to talk about those kind of separately. And then we also have hair follicle receptors. So you actually have receptors that wrap around the hair follicles. And so if something if something were to rub up against this hair and move that hair, you have these receptors that detect that movement, okay? And these are rapidly adapting as well. And we'll talk about why that is. And then we have all of these encapsulated receptors that we'll talk about. So we've got Meissner's corpuscles, Pacinian corpuscles, again, all encapsulated. We haven't talked about the bulbous or Ruffini corpuscles, but they're in a capsule as well. We'll talk about those. These muscle spindles that are going to wrap around these muscle fascicles are going to be encased also in a corpus or in a capsule, some type of capsule, usually again a tendinous sheath capsule. And then we have our tendon organs. And we kind of talked a little bit about those, but they're also, again, going to be in a capsule as well. You can kind of see that they drew this around here. And then our joint kinesthetic receptors. So we're going to talk about all of these. So let's talk about our non-encapsulated free nerve endings. Again, these are really abundant in our epithelial tissue, especially our skin tissue, and then some of our connective tissues. Most are non-myelinated. They're small diameter group C fibers. Not necessarily super important for you to know this, but it helps us understand that they are fast adapting. But again, not critical. That I'm not going to test you. I'm not going to ask you, is your non-encapsulated nerve ending non-myelinated, or what type of diameter is it? I just want you to know that these non-encapsulated free nerve endings are going to be the ones that you're going to be primarily finding in kind of your epithelial tissue that are going to detect things like pressure, things like temperature, like cold or heat, things like pain and itch, okay? So they're going to respond mostly to those: temperature, pain, light touch, or itch. So this is kind of the big portion that I want you to know. So let's talk about some of these different specific types of receptors. So let's talk about thermoreceptors, because thermoreceptors are kind of interesting. Believe it or not, we actually have separate thermoreceptors that are cold receptors versus heat receptors. And our cold receptors are going to be activated by temperatures from 10 degrees Celsius to 40 degrees Celsius. Or for those of you that don't think in Celsius, it's going to be, around 50 degrees Fahrenheit to 105 degrees Fahrenheit. which is a pretty big range. You may be like, well, that's a really big range for cold receptors. And wow, cold receptors don't go very cold. They start at 50 degrees Fahrenheit. So what happens when it's 32 degrees outside, freezing temperatures, or if it's even 40 degrees Fahrenheit outside? You know, I was just recently in Flagstaff and it was, you know, in the 30s in the morning. And so you may say, well, what's happening? Our cold receptors can't detect that because, you know, they start at around 10 degrees Celsius or 50 degrees Fahrenheit. And so we're going to talk about, what do you think is going to detect temperature below 50 degrees Fahrenheit? Any ideas? I'm pretty sure some of you probably have it already. And if you said nociceptors, you're correct. So below 10 degrees Celsius or 50 degrees Fahrenheit, they're the same thing, right? So below that point, your pain receptors are activated. And that's what tells you that it's really cold at that point, okay? So kind of interesting when you talk about, and that's partially, you know, a protective mechanism, right? Because as you're approaching, you know, these freezing temperatures, your body wants to trigger its pain receptors so that you don't actually freeze your tissues. So it's pretty smart. Your body's smarter than you might think. Okay, so those are the cold receptors. Again, they're activated with temperatures between 50 degrees and 105 degrees Fahrenheit. Again, they're located in your kind of superficial dermis, in the upper portions of your dermis. And then the heat receptors are going to be activated by 32 degrees to 48 degrees Celsius. And again, for those of you who don't speak Celsius, that is going to be 90 degrees Fahrenheit to 118 degrees Fahrenheit. And you may say, well, it hits 120 degrees outside here. What happens after, you know, you have 120 degrees Fahrenheit? And so 120 degrees Fahrenheit, again, is that point above which you're going to trigger, you got it, your nociceptors, okay? Again, you're going to trigger those pain receptors above 48 degrees Celsius or above, you know, 118, 119 degrees Fahrenheit as a protective mechanism. Because again, it's getting really hot and now you can actually do damage to your tissues, okay? So pretty interesting. Outside those temperature ranges, again, here we go, nociceptors are activated and interpreted as pain. So kind of interesting in how we detect temperature. I think it's fascinating because it's not as simple as everybody might think it is. Nociceptors are, okay, of course, we've already talked about them, are pain receptors. They can be triggered, of course, by extreme temperature changes, or again, something that actually might potentially cause damage to your tissue, like pinching you really hard, or release of chemicals, especially inflammatory chemicals from a damaged tissue. So those are the types of things that are going to trigger nociceptors. And so we have these vanilloid receptors, and this is part of what makes up your nociceptors. The vanilloid receptor is actually just a protein, and it's a protein in your nerve membrane. That's actually the main player for these nociceptors. So the vanilloid, I don't really like to call it vanilloid receptor because it sounds like it's a receptor within a receptor. It's actually a protein. So if you want, you can call it vanilloid protein. That's in, again, the membrane of that nociceptor. And it acts as an ion channel that's opened by, again, high extreme heat or extreme cold, low pH, or, certain chemicals like inflammatory chemicals that might be released. Or another one is capsaicin. I don't know how many of you know capsaicin, but that is what makes peppers. That's the chemical that makes peppers taste spicy to us. And we haven't gotten to this, but when we get to this, it's really interesting. You actually don't have a receptor when you're talking about taste receptors. Like, you have a sweet one, a receptor for sweet, a receptor for bitter. You don't have one for spicy. Guess what it is? Got it. It's a nociceptor. It's a pain receptor. So if you can eat spicy foods, it's because you actually lack some of those pain receptors on your tongue. So for example, I cannot eat spicy foods. And so when I eat that capsaicin, okay, in peppers, it activates all of my vanilloid proteins, right, in my nociceptors, and I feel pain on my tongue. Versus my husband could eat peppers all day long. And so I always tell him it's because he's deficient. He's deficient in pain receptors, nociceptors, on his tongue. And so he doesn't have this sense of pain when he eats the capsaicins. So kind of interesting. So again, those capsaicins will bind again and to that vanilloid protein in that nerve membrane and open up that ion channel. So basically the vanilloid protein is an ion channel, okay? And it's in these nociceptors. Also, we have itch receptors in our dermis as well, and they can be triggered by chemicals, and you can probably guess it's triggered mostly by histamine if you've ever had, an itch. So again, you can see here when a mosquito, when it goes to feed on you, it's actually injecting some irritants as well into that tissue, and that is going to stimulate an immune response and mast cells to release histamine. And so when that histamine is released, it's going to, again, trigger these itch sensory receptors, and that's what gives you that sensation of itch, okay? So kind of interesting. And what's interesting is the sense of itch is very similar to actually the sense of pain. And because of that, I actually have this issue with my son. He has some inflammatory disorders, and he's basically produces lots of histamine. And so because of that, he had some major issues with eczema, and he couldn't sleep at night. Like he could never get to sleep until they found a new medication for him. But so it was really bad for him in terms of development when he was younger. And so we actually ended up working with a pain psychologist who helped us deal with itch, because itch can be dealt with in a similar manner to pain. So kind of interesting. It's my personal experience with itch and pain there. More about non-encapsulated free nerve endings here. So again, we have those tactile Merkel discs. Remember those that are, again, those tactile Merkel discs you're going to find also in the upper dermis, oftentimes right along the boundary between the dermis and the epidermis. So here you can see, here's your Merkel cells here, okay? Merkel disc, and again, this is a light touch receptor, okay? So this is just detecting if you just kind of barely rub up your skin with your finger, then you're activating those Merkel cells, okay? And so again, they're located kind of, they say deeper in the layer of epidermis. I like to think of them at the border of the dermis and epidermis. They're usually right at the border there. Hair follicle receptors. Again, remember, these are going to be these receptors that wrap around the hair follicles. And so this is going to detect, again, the light touch or movement of hairs, okay? So if you just rub your finger, not across your skin, but just across your hairs, you can feel that. So try that, just even if you have longer hairs on your arms or something like that, or on your legs, just rub your finger right across those hairs, and you can feel that touch, even though you're not touching your skin. And that's because of these hair follicle receptors. This is important because this is what allows us to feel a fly landing on us, right? So sometimes we can feel a fly as it moves our hairs on our arm, or a mosquito, okay? So it will allow us to detect that light touch in terms of the movement of our hairs, okay? So kind of cool. And this was just kind of interesting on mosquitoes and talking about, you can kind of read this on your own. I kind of put this in just for fun, but it talks about mosquitoes kind of as they pierce through the skin. They have to kind of pierce through the epidermis and through kind of several layers. And so it talks about they end up secreting anticoagulants to kind of keep your blood from clotting. And when they do that, they also secrete other things, and that triggers that release of histamine. So that's why your mosquito bites end up itching. So then that histamine, again, is going to trigger those itch receptors, and that's what's going to cause mosquito bites to itch. So just kind of interesting. Encapsulated dendritic endings. So now we're going to talk about these ones that are in capsules, these receptors that are in capsules. So these are going to be like your Meissner's corpuscles, your Pacinian corpuscles, your bulbous corpuscles or Ruffini corpuscles, muscle spindles, tendon organs, sorry. I can't talk today, and joint kinesthetic receptors. So all of those are going to be your encapsulated ones. So Meissner's corpuscles, as you probably remember, these are going to be, remember, in those dermal papilla. I know this is taking you way back to the beginning of the semester, but those Meissner's corpuscles are going to be right up here. Let me see if I can find here. Here we go. Here's Meissner's corpuscles right here in those dermal papilla. And those guys are right up along the border of the dermis and the epidermis. So just below the skin, and I shouldn't say below the skin, because technically the dermis is part of the skin. We should say found just below the epidermis. So technically that's not correct, but it was actually out of the textbook. But technically it's found just below the epidermis. So it's mostly in, again, your sensitive hairless areas that you're going to find this, like in your fingertips. So this gives us our kind of discriminative touch in our fingertips. It a lot of times will allow us to tell whether or not we're rubbing something that's maybe smooth in our fingertips versus rough in our fingertips. So it gives us this discriminative touch of what we're feeling, what that sensation is in these hairless areas. Now, our Pacinian corpuscles, as you remember, are way down here, okay? Also called lamellar corpuscles, but I'll call them Pacinian corpuscles because that's what I called them for the lab, as well as the integumentary system. And these, again, are going to be these larger receptors. They're going to kind of look onion-shaped, and they're going to respond to deep pressure and vibration when it's first applied, okay? We'll talk about why it's when it's first applied. So when you first push on your arm really hard, when you first feel that pressure, okay, that sensation of pressure, that will be initially your Pacinian corpuscles, okay? Oops. Now, if you keep pushing hard on that same area, then you're going to trigger your Ruffini corpuscles or your bulbous corpuscles, which are going to be down here and kind of in between. And they're going to respond to kind of deep, continuous pressure. So again, Pacinian corpuscles would be kind of triggered first, and then your Ruffini corpuscles will be triggered for kind of more long-term pressure. Muscle spindles, we've kind of already talked about these because we had to talk about these when we did the reflexes, but muscle spindles are going to be these kind of spindle-shaped proprioceptors that are going to respond to muscle stretch when you stretch a muscle, okay? So that's why they were associated with some of those reflexes. And then our tendon organs, we talked about the reflexes as well. They're going to respond to stretch in the tendons, detecting stretch in the tendons. And then your joint kinesthetic receptors are just going to be these proprioceptors that are in the joint monitoring the joint position and motion, okay? So they're going to monitor, for example, if you close your eyes, if you want to know what your joint kinesthetic receptors do, close your eyes and then slowly open your hands. And I'm pretty sure you are aware of which joints are moving, okay, on your hand. So you know which joints you're moving, and that's because of those joint kinesthetic receptors, okay? So kind kind of cool. All right, so let's get into a little more on, now that we've talked lots about sensory receptors, let's talk about how we get from sensory receptors and activating those to sensation and perception. Remember, sensation is going to be this awareness that a change has occurred either in your internal or external environment. And that's because, again, as those sensory receptors are activated, they have to send that information, right, through sensory receptors back to that primary somatosensory cortex. That's where sensation's going to happen, okay? You're like, oh, okay, there's, I felt a touch there, yeah. Or, oh, pain there, somebody's pricking me with a, pin. Now, perception is going to be your conscious interpretation of those stimuli. So again, let's go back to if someone's pricking with a pin. Your sensation is pain, okay? Your perception is, hey, that they're pricking me with a pin there. That hurts. I want to stop that, okay? And that perception is occurring, that kind of conscious interpretation of that stimuli is occurring in that somatosensory association area that's back here, okay? So that's happening in these association areas. So that's sensation and perception. Make sure you know the difference between those two. So our somatosensory, again, system is part of that sensory system that's going to be serving the body wall and the limbs. And it's receiving, again, our input. This is basically what we've been talking about the whole time. Exteroreceptors, proprioceptors, and interoreceptors. And again, that input is being relayed to that somatosensory cortex, okay? And then our somatosensory association areas. So when we talk about, again, these kind of levels of neural integration, again, we first are initiating things at the receptor level. So we're first initiating, again, a response in the actual receptor, okay? So here, the joint kinesthetic receptor is being, again, activated, or your muscle spindle receptor is being activated. Then the circuit level is processing that information in the ascending pathway. So then that information is then sent, right, through these sensory neurons. And where they're sent here, okay, they can go to different places. Where they're sent here is part of that circuit level processing. And then the perceptual level is when we're going to be processing that information in cortical sensory areas. So again, we're coming up here to the somatosensory cortex, and that information is getting sent back to the somatosensory association area. So we can really process, we can do our sensation and our perception of that sensory response. So those are kind of the main. I'm not as concerned with that. I more would like you, instead of knowing these like receptor level, circuit level, perceptual level, I'd rather kind of know that we first trigger a receptor, that information is then sent back through the peripheral nervous system, through sensory neurons, into the central nervous system. And of course, again, it's going to go to the somatosensory cortex for your processing. Well, and this is, again, somatosensory if it's coming from the body, if it's not one of the special senses. And then the somatosensory association area for your perception. Processing at the receptor level. So again, of course, we kind of already talked about this. You have to generate enough of a graded potential, right? So to get that receptor, okay, to then excite and trigger an action potential, we have to get enough of a stimulus that has to excite that receptor enough to trigger an action potential, or the release of neurotransmitter that will trigger an action potential, okay? So the stimulus energy must match the receptor specificity, meaning touch receptors can't respond to light, okay? Your photoreceptors aren't responding to sound, okay? That's pretty easy. The stimulus must be applied within the receptive field. So, obviously, if you can, you can be miles away and trying to talk to me, and you're out of my receptive field. I can't detect you talking from miles away. Okay. And then transduction must occur. So the energy of that stimulus is then going to be converted into a graded potential, right? That we call our generator potential. Or again, receptor potential, which we'll get to when we talk about special senses. Okay. So that big idea here is that, again, in those receptors, you're getting graded potentials. And enough of those graded potentials, okay, sum up together to trigger an action potential. Okay, they meet threshold, then you trigger an action potential. Okay. So that's just kind of a review of what we've already been talked about. Now let's talk about adaptation. So sensory adaptation is, and you all probably intuitively know sensory adaptation, but this is a change in your sensitivity in the presence of a constant stimulus, okay? So some receptor membranes become less responsive with a constant stimulus. And this is what you're seeing in what's called a phasic receptor. We also call them our fast adapting receptors. So you're getting this constant stimulus at a constant, rate. And so basically, eventually, this receptor becomes less responsive to that. So it's called a fast adapting one. So it'll send, in the very beginning when this stimulus is applied, again, it will send signals at a much faster rate. And then it'll kind of start to slow down. It's like, yeah. I feel that shirt. I know. Yeah, that shirt's been on for, the last 5 minutes. I don't really care about it anymore. So that's kind of what our phasic receptors are doing. So a lot of these are receptors for pressure, touch, smell. So you may have noticed this if you've ever walked into a room that had kind of a strong scent. And then as you sat in that room for a while, you're like, I don't smell that. I don't know if you guys have ever, studied at a coffee shop, right? And you walk in and you're like, oh, it smells so good, the, coffee shop. And then by the end of it, you don't really notice the smell. But then you leave the coffee shop and you smell your shirt and you're like, whoa, I smell like coffee shop. That's because, again, your sense of smell has these phasic receptors. They're fast adapting. And so, again, you apply that constant stimulus and the receptor membranes become less responsive. Now, in a tonic stimulus, these are slow adapting. So sometimes they adapt slowly or sometimes not even at all. So, you apply your stimulus and you get that kind of same response, okay, for that stimulus. And this is going to happen most commonly in your nociceptors, your pain receptors. And this makes sense, right? Because if someone's applying pain in an area, your body wants to protect that area, so it doesn't want to ignore that pain, right? And so that's one of the reasons why your nociceptors are what we call a tonic receptor. A tonic receptor is going to keep the tone of the response to that stimulus, okay? So most nociceptors and proprioceptors are an example of that. So let's talk about some sensory adaptation, okay? Do you feel your underwear all day? Probably not, right? You might feel it when you first put them on. That's because those sensory receptors that you have for that sense of tactile touch in those areas are going to be your fast adapting phasic receptors, okay? That's why you don't feel your underwear all day. That's why you don't feel your shoes all day. When you first walk into a room and you hear the heat, it's really loud, or you hear the air conditioning, mostly air conditioning here, right? The reason that you don't notice it the whole time, or it doesn't bother you, right? It might bother you when you first walk in the room, but then after that, you 5 minutes into it, you don't even notice it. Again, that's because of that sensory adaptation. Again, those phasic receptors have become kind of numb, basically, right, to that constant stimulus. So kind of interesting. And this is just a funny meme on this, talking about your adaptation to a fan, sensory adaptation to a fan. Also, if you've ever, maybe you have someone that wears strong perfume, and when they first walk into the room, you're like, whoo, that's really strong. But then again, 5 minutes later, you don't really notice it. Again, that's an example of sensory adaptation. So some major features of sensory perception. We have what's called, our perceptual detection. This is our ability to detect that a stimulus actually has occurred, okay? And usually we get input from several different receptors that are put together for our kind of perceptual detection of a stimulus. So for example, if your fingertips feel cold, you're probably, again, getting for this ability to actually, have that awareness that your fingertips are cold and that you should do something about it. You're probably getting information from nociceptors, from thermoreceptors, okay, from different receptors here. Magnitude estimation is just the ability to detect how intense that stimulus is, okay? Is it a lot of pressure or is it a little bit of pressure? Spatial discrimination is just like it sounds. It allows us to identify the site or pattern of stimulation, okay? And this often depends on how many of those receptors you have in a certain area. So, for example, if you want to understand spatial discrimination, I want you to take some tweezers and I want you to have a roommate, okay, do this 2-point discrimination test on you. It determines how close together 2 points on the skin can be detected and still perceived as 2 separate points rather than 1. And this distance is going to vary from like 5 millimeters in highly sensitive areas like the tip of your tongue to more than 50 millimeters on less sensitive areas on your back. So, do this and you have to turn around and not look, and your roommate can, pull those tweezers closer and closer together until you cannot detect those 2 points anymore. You just detect 1. So have your roommate do that on your back versus like the tip of your finger or even your arm. And you're going to notice that you can have a much larger, wider distance on like your back and your less sensitive areas, right? Versus, your finger or something like that. So your finger's actually, going to be closer like 5 millimeters. They'll be able to detect that 2-point discrimination, okay? Versus, on your back, again, it's going to be a much wider distance. So kind of interesting. Try that out, and that's your 2-point discrimination. So it's a fun test to be able to do that. So you could do this again. Here's the 2-point discrimination test. But try this. Do it on your tongue. You can usually still detect those 2 points as 2 points, just 1.1 millimeter away on your tongue. About 3 to 8 millimeters on your fingertips. And then on your back, look at that, it's 36 to 75 millimeters. Wow. So again, you might be by 36 millimeters, you're probably only detecting 1 point, even though you're hitting 2 points that are 36 millimeters apart, okay? Because again, though, the density of those receptors is much less than it is on your fingertip, which makes sense. You want your fingertips to be, again, used for more fine motor skills and things like that. So you need good, sensory discrimination there. So anyway, kind of interesting. Just a fun test. Try this. Major features of a sensory reception, okay? Feature abstraction is just our ability to identify more complex aspects of a stimulus. So I put a picture of my dog up here. And if you reach down and you rub your dog, okay, one touch of your dog's fur is going to give you lots of information about your dog's fur. One, you detect, okay, it's warm, but their hair is kind of coarse and short, but it's flexible, the hair can move. So this is feature abstraction. All of the sensory perception is being processed together for this one perception of our sense. So it's actually multiple receptors that are sending all this information back to, that same area in the brain, and that gives you your perception of your dog's fur, okay? That's feature abstraction. So just taking, again, these really complex aspects of a dog's fur and putting it all together, being able to discriminate it. So that goes along with quality discrimination, our ability, again, to identify kind of submodalities of a sensation. So, for example, you can be able to detect sweet versus sour. That's quality discrimination. And then pattern recognition is just your ability, again, to recognize these kind of significant patterns in stimuli. So again, something like, the melody of music or something like that. So again, just a pattern of that stimuli. Now, lastly, here we're going to talk about pain a bit, and our perception of pain. And the reason is that pain is quite important. Remember that it's going to be one of those tonic receptors, and so it's going to be really slowly adapting. And that's important because we don't want to adapt to pain, because pain is what's warning us of, some impending tissue damage. So this is our body's own protective mechanism. And impulses will travel, again, remember, on these fibers and release neurotransmitters, glutamate and substance P, for perception of pain. Substance P being the big one. Glutamate's excitatory, of course. So we can have visceral pain, which is, of course, pain in, coming from our organs. And that's going to result from, stimulation of pain in our organs. And then we can also have, from that, referred pain. So most of our visceral pain actually comes out as referred pain. So pain from one body region perceived into another area. So a lot of times, you're not like, oh, I feel pain. Oh, that's definitely liver pain right there. I feel my liver in pain. You don't. You actually will feel the referred pain from the liver, oftentimes up in this kind of right upper quadrant area, even into the kind of thoracic region a little bit here, or in your right shoulder here, okay? This is why oftentimes if you have an intense pain in your left shoulder, and you kind of meet the right qualifications, they may look at you for a heart attack. And that's because the heart pain is referred, again, to this kind of left upper chest region and shoulder. And then even down, a lot of times a person that's having a heart attack will say they have a pain in their left upper shoulder and it radiates down their arm. And that's a good indicator that, again, they're having some type of issue with their heart, and that's the referred pain. So kind of interesting to see some of this referred pain, again, and where it's referred to throughout the body. So just kind of interesting, but really very important clinically to understand, why pain in the left shoulder radiating down the left arm is a good indicator of a heart attack. So those types of things. Sometimes people that are having a gallbladder attack will have pain in their right kind of upper shoulder here. And then usually, again, in that kind of right upper quadrant as well, where the gallbladder actually is located. So again, lots of referred pain there to look at. Now, your perception of pain. How come it is that, let's say you were being chased by an attacker and you happen to fall and scrape your knee and it's just bleeding everywhere, and you get back up and you run from your attacker? Why is it that you don't really notice that pain until you stop? And I even have noticed this, honestly, even just running. Like, I've been, running before, and I fell and tripped and scraped up my knee, and then, got back up and ran the rest of the race. And then at the very end of it, I was like, oh, that kind of hurts, actually. And that's because, again, remember, especially when our sympathetic nervous system is stimulated, we have our own pain-suppressing endogenous opioids that we release. Remember those endorphins and the enkephalins? And again, our endorphins are naturally released when we're doing things like running. Again, because that's kind of triggering that sympathetic nervous system. You're like, oh, you're running. Maybe you're running from a scary person. We better release endorphins so that you keep running, because we don't want to stop running just because we feel pain, right? Because we got to get away from whatever that source is. Even if, you're just running a race, your body doesn't know that. So it's kind of interesting. So remember these endorphins can be released, and they actually will end up blocking your pain reception. They'll end up binding to these little receptors on the opiate receptor here, and or on the presynaptic membrane here, and they'll actually block the release of substance P here. So here they'll bind here and then block that release of substance P, shutting down that pain response. So there's an actual reason why. Again, if you're running a race, you can finish the race, and then it's not until the very end of the race that you're like, oh, it kind of hurts. So thank those natural endogenous opioids, endorphins, and enkephalins for that. Now, you may think that, like, are there conditions where, and I know you know of them, where there are people that are born without the ability to feel pain. This is actually, there's a term for this. It's called congenital insensitivity to pain and anhidrosis. Or sometimes they just call it congenital insensitivity to pain, CIP. So you'll hear it called CIP or CIPA. And this is an actual congenital condition that you're born with. And these kids don't have the ability to feel pain. It actually has to do this more than you have to know, but it has to do with this malformed ion channel that actually impairs the transmission of the pain signals, because that ion channel won't actually properly function and open like it should in response to like substance P. So what ends up happening is these individuals don't feel pain at all, which may seem really cool and may seem like a superpower. Like, oh my gosh, what would it be like to never feel pain? But I implore you to watch this video, even maybe just the first like 5 minutes of the video, and you will see why it's really important for us to feel pain. Because you're going to hear some stories like one of the girls talks about she just was making dinner, wasn't even thinking, and her spoon dropped in there, and she just stuck her hand into the boiling water to grab the spoon out. Because again, there's not that fear of sensing pain because they've never sensed pain. One of the little girls, you'll see her tongue is all malformed. It was because when she was teething, she would bite her tongue so hard because as a baby, you know, you couldn't tell her not to bite her tongue just because she couldn't feel pain. And she couldn't feel that pain or biting her fingers. So again, really interesting story. Please just spend a few minutes watching that. Just click on that, watch that, and it really helps you to understand why we have pain. They're also studying these children with this congenital disorder to see if there's a way that they can help people with chronic pain, to help kind of find a balance to where they can maybe study these people without pain and figure out how they can lessen the pain of some of these chronic pain individuals. Okay, so this is just going to talk a little bit about now I'm not going to talk a lot about this, our transmission lines or nerves and kind of their structures in repair, and mainly because we've already kind of talked about this. So I talked about our structure of our nerves. So we have the endoneurium. Remember, the endoneurium covers each individual axon. It's connective tissue that covers each individual axon. And then we have the perineurium, which is going to, surround fascicles or bundles of nerves. And then we have the epineurium, which is going to go around the entire nerve. Okay. So just kind of as a review, you can see all that there. And most of our nerves, again, are going to have a mix of sensory and motor nerves. But we do have some that are primarily just sensory nerves, and we have some that are just motor nerves. But most, again, of our nerves are going to be mixed nerves that have, both sensory and motor bundled together. And so keep in mind that if there's damage to a nerve, especially the axon of a nerve, in the peripheral nervous system, it may regenerate. Remember that? But in the central nervous system, it will not. And that's because we have Schwann cells, remember, that would form that neural tube. for the regeneration tube in the peripheral nervous system. Oligodendrocytes can't do that in the central nervous system. So that's just a kind of a reminder. I wouldn't necessarily test you on this here because it was back from when we did the nervous tissue chapter, but I just wanted to remind you that that's why you can see, again, some gaining back of function if damage was in the peripheral nervous system, but if damage is in the central nervous system, you're just not likely to regain that function back because we don't have the regenerative capabilities in the central nervous system. So again, only in the peripheral nervous system do we get that. And this was just kind of a reminder that, again, you could have that regeneration in the peripheral nervous system. If, again, the cell body. If the cell body's damaged, then it's, it's game over if you've really damaged the cell body. But if it's the axon, then again, they can form that regeneration tube, and you actually can get some repair of those axons. Cranial nerves, again,